Hey guys, Ms. Thomas here. This is the asynchronous recording for Business Math A, Unit 3. Today we're going to take a look at Lesson 12, Modeling Data with Functions to Find the Best Buy, and from Lesson 15, Computing Average Daily Balance and Finance Charge. Remember, if you want to see additional examples either on these topics or on things, for example, from lessons 11, 13, or 14, go to the recording library. I have a full Unit 3 video and several short workbook help videos available. Let's get started with lesson 12. So again, we're going to practice modeling data with functions and finding the best buy and evaluating bargain shopping. So this is actually a really practical lesson, and it teaches you a couple of terms and a couple of skills that I think will be helpful to you in your day-to-day shopping. So first, let's take a look at unit pricing. This is a technique that allows shoppers to compare the price of various items. Let me give you an example. Recently, I went to the store and I needed to buy olive oil, but I found it difficult to figure out which one to buy because, of course, there were these different size bottles of olive oil, right? So there was like a small, this will be my bottle, a smaller bottle, and then there would be like a larger bottle of olive oil, and then like a mega bottle, and then some of them the price was given per ounce. Another one, I think the price was given per gallon, etc. So it made it difficult to kind of figure out what's the best buy I'm getting here. With unit pricing, you determine what unit you want to set everything to, and then it allows you to compare across items regardless of what size, etc. They might be different in. Sales tax is a state or local tax on the selling price of an item, usually expressed as a percent. So I think we're all familiar. If I bought my olive oil and it was marked for $19.99, when I go to the checkout, I'll probably end up paying like $22. That extra money that's tacked on there is my sales tax. And that full price, that $22 or so, that's the total purchase price. It's my selling price plus my sales tax. Comparison shopping is related to what I just discussed up here with this example, and it's just when you compare prices to figure out what will have the best value. So let's do an example of unit pricing. This is not going to be the focus of this video, but I do want to do one example as sort of a warm-up. So let's say that Jackie can buy 12 cups of noodles for $3.48, 20 cups for $5.40, or 50 cups for $11, and we want to know what's the best buy here. So the assumption is that the best buy is going to be based on price. So of course you might be thinking, well, I don't even want 50 cups. I would never use them. They might go bad, things like that. That's not what we're considering here. We're just focusing on price. And what we're going to do is we're going to use unit pricing to determine what the best value is. So if I want to know the unit price, this is what I mean. Notice that this price, $3.48, is based on 12 cups, and similarly this price is based on 20, this $11 is based on 50 cups. The best way for me to compare these is going to be to ask myself, well, what am I really paying per cup in each of these situations? So I'm going to take the item price and divide by the number that I'm getting. So for example, if the price is $3.48, I'm going to take that price and I'm going to divide by 12. That's the total number of cups I get for that price. And that tells me that I'm going to end up paying 29 cents each per cup. And then I would do the same thing with 20 cups. I'd take the price, $5.40, and divide by the number I get, 20. And it turns out I'm paying about 27 cents a cup. And the same thing with 50 cups. I take $11 divided by 50. I'm paying 22 cents a cup. So you can see that the general trend is that the more you buy, the lower the unit price gets. And this is often true, not always. I have seen stores that will do the opposite thing for some strange reason, but in general, you can expect that the more you buy, the bigger the bulk, the lower the unit price, right? So in this case, we do find that the 50 cups end up being 22 cents each, so that's going to be the best buy when we're using unit price as our criteria. Okay, so that is an example of evaluating bargain shopping algebraically. The next couple examples and the focus of this video is going to be on using systems of linear equations to evaluate buying options. And this is when payment is a little more complicated than just saying, something costs $5. And you'll see what I mean in the next slide. So remember that a linear equation is something that looks like this, right? So it has a variable that only has a exponent raised to the first power, so there's no x squared, x cubed, anything like that. If I were to graph a linear equation, the graph of this function would be a straight line. I don't care what direction it's going in, as long as it's a straight line, it's linear. So a system of linear equations is just when we're considering more than one equation at once. Okay, so that could be, a system could just be those two equations, or it could be all four of these equations, it could be three of them, whatever. Let's also review the parts of a linear equation. So in general, the most helpful way for us to kind of analyze these, especially for this topic, is going to be to look at things in slope-intercept form, which looks like this: y equals mx plus b. And hopefully this will be a review for you. Remember that m stands for the slope, the rate of change, the rise over run, or the steepness of the line. And b is the y-intercept, the point at which, if I have a function, it's the point at which this function is crossing the y-axis. And similarly, I could mention the x, this is the x-intercept, the point at which the function crosses the x-axis. But for this equation, we really only need to know about b, the y-intercept. So the best way to get used to this, of course, is to practice. So we're going to go through a couple examples that will demand us to create systems of linear equations. And here's what we'll do. First, we're going to read the context, read the question, choose variables to represent our unknowns. We're going to create equations based off of that information, and then eventually we'll get to a point where we're solving for some unknown that they ask us for. Let me show you what I mean. So let's say that Marcus is comparing the costs of long-distance calling cards. And there's card A and there's card B. And card A says, okay, the cost is 60 cents to connect, and then 7 cents per minute that you talk after that. So as soon as you pick the phone, you're charged 60 cents, and then 7 cents a minute after. And that's card A. Card B is a little bit different. It's only 20 cents to connect, but then it's 9 cents per minute after. And again, that's card B. And we want to know, for how many minutes would Marcus have to use these cards in order for the cost to be the same? One more time. How many minutes would Marcus have to use in order for the cost to be the same on card A and card B? So, for example, I can see that if I used card A for 1 minute, it would cost me 60 cents to connect, plus the 7 cents for that minute. That would be 67 cents. Card B for 1 minute would be 20 cents to connect, and then 9 cents, it would be 29 cents, right? So what I want to do is sort of track at how many minutes do the costs equal each other. So at minute 1, it's 67 cents versus 29 cents, and I want to do the same things for minute 2, 3, 4, 5, 6, etc. You can see where doing this algebraically by hand would take a long time, right? So I could compute, 1 minute costs 60 cents plus 7 cents, 2 minutes costs 60 plus 7 plus another 7 cents, and then 3 minutes would be another 7 cents, and 4 minutes would be another 7 cents, etc., right? I could do that by hand, but chances are that that's going to take me a while. With all that algebra or all that kind of computation, I'm likely to make a mistake. It's better if we analyze this by making these into linear equations. So how do we do that? So we're going to choose variables to represent each unknown. Now, my suggestion is that x should equal minutes and y should equal cost. And let me explain why I am saying that. So when I read the question, first we have to recognize, what are our unknowns? Well, we don't know how many minutes Marcus is talking for, and we don't know what the total cost is. And if you weren't sure where I got those from, you could also read the final question which asked you how many minutes, so we know that's a variable, would Marcus have to use in order for the cost to be the same? And once again, we don't know that. That's another variable. I recommend making x your independent variable, minutes, and y your dependent variable. So the total cost depends on how many minutes you're on the phone for. Okay? Notice, though, that they did not tell us how many minutes Marcus is going to be on the phone for. It just said how many minutes for the cost to be the same. So it sounds tricky, but you'll see in a moment that it's actually not so tricky to figure out. But before we get to that, now that I've decided that x stands for minutes and y stands for total cost, I'm going to create equations, one to represent card A, one to represent card B, that give me this highlighted information in equation form. So first we have card A. So here's what I did. I have y equals, so the cost of making a call on this card, y equals x, the total number of minutes, times 7 cents, because it's 7 cents per minute, right? So I know that 1 minute would cost me 7 cents, 2 minutes would cost me 14 cents, 3 minutes would cost me 21 cents, etc. What am I doing to figure that out? I'm taking x, the number of minutes I'm talking, and I'm multiplying it by the cost per minute. So that's where I got 0.07x from. And then I'm adding on 60 cents because there's a 60-cent charge just to connect, right? So it's just a flat fee. I don't need to multiply it by anything. It's just a connection charge. So it doesn't matter how many minutes I'm talking for. As soon as I pick up that phone and dial, I'm charged 60 cents. Similarly, I can create an equation for card B. Remember, it says card B, the cost is 20 cents to connect. That's what you see represented here, just a flat 20 cents. And I'm trying to compute y, total cost, and then it says 9 cents per minute. So I'm going to take 9 cents and I'm going to multiply it by x, the number of minutes I'm on the phone for. If this doesn't make sense yet, I recommend pausing the video, taking a moment just to review, maybe even rewind and re-listen to it. I want you to really understand why these equations make sense for this situation. Now comes the part where we figure out how many minutes would Marcus have to use for the cost to be the same. Well, remember, y is representing cost in both of these equations. So if cost is the same, that means that y, these two y's, are equal to each other. If these two y's are equal to each other, that means that these two statements are equal to each other as well, and I can set them equal to each other. So I get that part in yellow that I had set equal to that part in red. I have 0.07x equals, or plus 0.6 equals 0.09x plus 0.2. Again, because I'm saying that the amount of minutes is the same, because I'm saying that the cost is the same, I set my two cost equations equal to each other. Notice now that I just have a one variable equation, and I can just solve for x from here to figure out where these are going to be the same, and I find that x equals 20. So it's going to take a 20-minute phone call would cost the same on card A as it did on card B. Let's consider this another way. So again, this is the same stuff from the last slide, but I want to graph the two equations to give you an idea of what we're solving for. So card A is the line graphed in black, card B is the one in orange. And I just plugged in these equations to my graphing calculator. Okay. So for A, again, y equals 0.07x plus 0.6. For B, y equals 0.09x plus 0.20. The goal was to find where cost was equal, where y was equal. Looking on this graph, that would be the same thing. Where do these y's equal each other? And you can see that the two y values are overlapping at 20. So if Marcus was going to have a 20-minute phone call, it doesn't matter which card he uses, it's going to cost the same either way. If he's going to talk for less than 20 minutes, you can see that the black line is below the orange, that means that the black, that the card A is cheaper from 0 to 20 minutes. But then on the other side, if he's going to talk for longer than 20 minutes, card B will be cheaper. And this has to do with the different flat rate, right? There's that connection rate. And then the cents per minute rates are different as well. So card A has a high connection fee but low cost per minute. So it makes sense that this is only going to make sense for a longer call. Cost B has a pretty low connection rate but a higher cost per minute rate, which is why it makes sense that card B would really only be better for short phone calls. But then they break even at 20 minutes. So in this question I asked, so what if he planned on talking for 45 minutes? And again, you can see that card A would be the better plan in that case. I'm sorry, that's incorrect. Card B would be the lower at 45 minutes. Card B would make more sense because the cost, the Y value, is lower. So this should be card B. Okay, let's do another example with a similar sort of construct. So say James has two different job offers at two dealerships across the street from each other. Honda is willing to pay him $1,500 per month and then $450 for every car that he sells. Toyota is willing to pay him $2,500 per month and then $350 for every car that he sells. So there's a difference in that flat base pay and then commission pay. So you can see how these are going to play out differently. One of them has a higher initial base pay, but one of them has a better commission. So the question is, how many cars would he have to sell per month in order to make the same amount? So let's check this out. Once again, we're going to choose variables to represent our unknowns. Well, what are our unknowns? Let's highlight. It says, how many cars would he have to sell per month in order to make the same amount of money? So our two variables are X, the number of cars being sold, and Y, the salary. And once again, notice that I've set Y equal to my dependent variable. That monthly salary is going to depend on X, my independent variable, the number of cars that are going to be sold. Now let's create equations to represent each dealership. So we've got Honda and we've got Toyota. So first, let's look at Honda. So it says Honda is willing to pay $1,500 a month. So the payment, Y, that monthly salary, Y, is equal to a base of $1,500 plus $450 for every car that he sells. 450x, 450 times number of cars sold. So this is the equation for Honda. And then we look at Toyota. Toyota is equal to, they're willing to pay him, remember total pay is Y, Y equals $2,500 per month, so that's that $2,500, and then $350 for every car, 350x, 350 times the number of cars he sells. We want to know at what point will our Y's, our total payments, be equal, so we set our two equations equal to each other. 450x plus 1,500 equals 350x plus 2,500. From here, solve for x. And we find that x is equal to 10. So if he sells 10 cars, he'll get paid the same amount whether he sells for Honda or Toyota. Now, notice that in our last two examples, the question has been a matter of setting equations equal to each other and saying at what point are our salaries, are our payments going to be equal. The question could also ask you, which one, like say James sells 15 cars this month, which one will give him a higher paycheck? So if they give you a number to actually plug in for X or for Y, you can evaluate it just the way you think you would. So in my example, I said, pretend he sells 15 cars, which place will give him a better paycheck? You would just sub in 15 for X, the number of cars sold, and then you could solve and compare. And the same thing for this other one, I could do 350 times 15 plus 2,500, right? I could do both of these, simplify them, and then compare that way. So again, most that I saw in your workbook and your checkpoint are of the kind where they're just asking you to evaluate where the two things will collide and overlap and be equal. And so for a lot of them, you're doing this type of setup. But occasionally they might ask you, to solve for a specific x, to solve for a specific y. Just plug in and solve accordingly. Okay, let's look at one last example. Let's say that Patrick is comparing the costs of renting bikes at the beach. To rent from store A, the cost is $5 to rent, then $2 per hour. To rent from store B, the cost is $8 to rent, and then $1.50 an hour. How many hours is the rental cost the same in each store? So in other words, for what number of hours would it cost him the same regardless of his choice? And hopefully you're starting to see the pattern in this question type. We're given two options to do something, and both options have this thing where there's sort of like a flat rate that happens no matter what. So for example, there's this base cost of $5, and then they give you this variable amount. So, this is $2 per hour. In the last example, it was depending on the number of cars he sold. The example before that, it was depending on the number of minutes he was on the phone for, right? So hopefully you're starting to recognize these patterns in this type of problem. So once again, we're trying to figure out what's the better option, plan A or plan B. So we are going to set up equations to figure this out. Now remember, try to make x your independent variable and y your dependent variable. So x, independent, the number of hours, determines y, our total cost, right? So our total cost that we're going to pay for the bike rental depends on how long we're on the bike for. Now there are a couple reasons that I keep reminding you of this. So one, it's always good practice to make x your independent variable. If you, for some reason, got your variables backwards and you solved, you would still end up with the correct answer. But in pretty much any math class you take, x is going to stand for independent. And when you start to look at textbook examples in the course player, they're going to set x as the independent variable. So it's just a good thing to kind of have in your toolbox, recognizing which one's independent and which is the dependent variable. Okay, so moving forward, create the two equations. So for store A, we have y equals 2x plus 5 because it costs $5 just to rent it. So we have that flat rate of $5 plus $2 per hour. $2 times x, the number of hours you're on the bike for. Solving that will give you y, the total cost of renting the bike. Do the same thing for your other plan. So plan B, the cost is $8 to rent, so $8 plus $1.50 per hour plus 150 times x, the number of hours we rent for, is equal to y, the total cost. Once again, we're asked how many hours is the rental cost the same in each store. So when are our y's going to be equal to each other? Well, let's set our y's equal and solve for x. So when I solve for x here, I'm saying that, there we go, x equals 6. So we're saying that if Patrick wants to rent a bike for 6 hours, it's going to cost him the same at store A or store B. If he rents it for less than or more than, he'll have to figure out which one makes more sense. But if it's for 6 hours, it doesn't matter which one he picks, he'll end up paying the same thing. Alright, so that's it for this video. Go ahead and continue on to your assessment questions.